Swayam Prabha. Digital India. Educated India.
Welcome to the lesson 6 of the course on strength of materials. In this particular lesson, we are going to discuss certain aspects of analysis of stress. We have already looked into certain aspects of stresses. In this particular lesson, we are going to look into some more aspects of stress analysis, and once this particular lesson is completed, one should be able to understand the concept of stresses in polar coordinate system. We will be able to understand the concept of stress for axisymmetric bodies, which eventually can be derived from this polar coordinate system of stresses, and also we will look into how to evaluate the stresses at different points. Hence, this particular lesson includes the recapitulation of the lessons which we have discussed already, evaluation of stresses in polar coordinate system, and examples for evaluation of stresses at a point in a stressed body. Now, before we go into the details of the evaluation of stresses in polar coordinate systems and others, let us look into the answers of the questions which I had posed last time. Now, the questions which were posed were: what happens to octahedral stresses when first invariant is 0? Now, let us look into if you remember that the stresses on octahedral planes which we had calculated, they are the normal stress sigma octahedral, which is equals to 1/3 of sigma 1 plus sigma 2 plus sigma 3. We had defined the octahedral planes as the planes which are equally inclined with the principal axis reference system, and thereby the stresses which are acting are sigma 1, sigma 2, sigma 3 in the rectangular stress system, and that the octahedral stress as we had defined as 1/3 of sigma 1 plus sigma 2 plus sigma 3, which is the summation of the normal stresses in 3-dimensional stress system, and we call this as first invariant. And if you remember, tau octahedral square was equals to 2/9 times sigma 1 plus sigma 2 plus sigma 3 square minus 6/9 of sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Hence, as it has been asked that if sigma 1 plus sigma 2 plus sigma 3 is equals to 0, then eventually the normal stress on octahedral plane sigma octahedral is equals to 0. So, if the first invariant is 0, then the octahedral normal stress will be equals to 0, only shear stress will be existing on the octahedral plane. Now, the second question which was posed was what is the value of the shear stress where maximum normal stress occurs, and the third question is what is the value of normal stress where maximum shear stress occurs. Probably these two questions we can answer through the same diagram. If you remember, last time we had shown how to plot the Moe circle. This is the sigma axis and this is the tau axis. Now, if we draw the Mohr circle of stress, the center of the Mohr circle from tau axis is given as sigma x plus sigma y by 2, and the maximum values of the normal stress which is at this particular plane, which we normally designate as sigma 1, and the minimum value of the normal stress is sigma 2. So, if you note that in these two planes where the maximum and the minimum normal stress act, the value of the shear stresses are 0. So, the planes where the maximum normal stress acts, the values of the shear stresses are 0, and these planes we call as principal planes, as we have seen in other lessons. And the third question, that the plane where maximum shear stress acts, what is the value of the normal stress? Now, this is the plane where, or these are the planes where the maximum shear stress acts. This is the maximum positive shear, this is the maximum negative shear. Now, if you note, and the value of the maximum shear stress is that of the radius of the Mohr circle, is tau max. If you note here that at this plane we have the normal stress which is equals to this particular magnitude, which we know already, which is sigma x plus sigma y by 2. So, from this diagram itself we can answer both the questions, where the planes where your normal stresses are maximum, the shear stresses are 0, and the planes where shear stress is maximum, their normal stress exists, and the value of the normal stresses are sigma x plus sigma y by 2. Well, after looking into these questions, now let us look into the aspects to how to evaluate the stresses in polar coordinate. Now, so far we have discussed about the stresses, the rectangular stresses in a body where we have assumed that the boundaries are straight boundaries. Now, there are several cases where other than the straight boundaries we get problems, we get structural elements where the surfaces are curved, and to represent the stresses on those curved surfaces, it is ideal to represent them in terms of a coordinate system which can be expressed in terms of radius and the rotational angle theta, which we call as the cylindrical axis or polar reference axis. Now, let us look into that. If we have a cylindrical body of this particular form, in this we have earlier seen the reference axis system as x, y and z. Now, if we select a point here on this body, let us say this is P, the coordinate of this particular point can be described by these coordinates x, y and z. Also, this particular point can be represented through another reference system, which if we project this point on this y x z plane and draw a line over here, this particular angle, if we define that as theta, and if this projected length is the radius vector r and this distance is y, then the coordinate of this particular point can be expressed as a function of r, theta and y. And this reference, this is with reference to the Cartesian system x, y and z, and this particular reference is with reference to the polar coordinate system, which is r, theta and y. Now, if we look into the plan of this particular, if we take a cross section of this, then if we draw two radial lines from the center, Let us say this particular radial line is at an angle of theta, and these two radial lines makes an angle of small angle d theta. Now, if we take a small element over here and if we try to look into the stresses that will act, so we will have two planes. This particular plane, normal to this plane, is in the direction of the radius, and we call this as r plane. Over these we will have the stresses which is acting is the normal stress, and so is this, which we call as sigma r. The stress normal to this surface which will be acting along the circumferential direction, we call that as sigma theta. Also, we will have the tangential stress on this plane as well as on this plane, and we will have tangential stress in the radial direction as well. And this tangential stress, which we have defined as shearing stresses, is tau on the r plane acting in the direction of theta, we call that as tau r theta, and other tangential stress on the theta plane will be tau theta r. Eventually, tau theta r is equals to tau r theta, as we have seen in the previous lesson. So, we define the state of stress on this particular body at a point is equal to sigma r, the radial stress, the tangential stress is sigma theta, and the shearing stress is tau r theta. Now, let us look into that if a particular body at a point is subjected to these stresses, then how do we arrive at the equations for equilibrium. Now, here I have tried to represent the state of stress at a particular point in a stressed body, and as we have designated that this particular stress which is acting normal to the r plane, let us call that as sigma r. Let us assume that this particular distance is dr. The first radial line, let us call this is at a distance of theta, and the small angle which is being made by these two radial line is d theta. The radial distance from the origin to the first part of the element, let us call that as r. Hence, the stresses which are acting, sigma r is the normal stress, the tangential stress as tau r theta, and the circumferential normal stress as sigma theta. So, the stress which is acting on this surface, since it is at a distance of dr, and as we have seen earlier while deriving the equilibrium equations at a particular point with reference to the rectangular Cartesian axis system, that if you try to find out the stress at two different points, then there is incremental stresses which is sigma r plus del sigma r del r over the distance dr. Likewise, the tangential stress, which is the shearing stress, is equals to tau r theta plus del tau r theta del r over the distance dr. On this we have sigma theta. So, on this particular surface, the tangential normal, the normal circumferential stress is equals to sigma theta plus del sigma theta del theta over d theta, and the shearing stress which is acting on this surface, this is the shearing stress on this surface is tau r theta, and this is equals to tau r theta plus del tau r theta del theta over d theta. Also, if we draw a tangent at this particular point, please note that the normal stress on this surface makes an angle of d theta by 2. Now, if we take the equilibrium of the forces in the radial direction and tangential direction, we can get the equations of equilibrium. Now, on this particular plane, the area on which this particular stress acts is r plus dr times d theta being small. This particular length we can write as r plus dr d theta, and this particular length as equals to r d theta. And if we assume the thickness of this particular element perpendicular to the plane of this board as unit, then area of this particular surface is equals to r plus dr d theta multiplied by 1, and this multiplied by the stress will give the force in this particular plane. Similarly, the force on this particular plane will be sigma r multiplied by r d theta times 1. Also, we have the stresses the tangential stresses on this surface which are in the radial direction, and sigma theta will have component in the tangential direction, also in the radial direction, and the component in the radial direction will be sigma theta times sine of d theta by 2, and d theta being small, we can approximate sine d theta by 2 as equals to d theta by 2. So, if we write down the equations of equilibrium in the radial direction, then the equations which we get, sigma r plus del sigma r del r into dr is the normal stress on the outer plane multiplied by the area which is r plus dr times d theta minus the normal stress which is acting on the first plane where sigma r acts is equals to the sigma r is the stress times r d theta times 1 is the area. So, this is the force. Then the shearing forces which are acting in the theta plane are plus tau r theta plus del tau r theta del theta acting over the length d theta and the area is dr minus tau r theta over the area dr times 1 minus corresponding to the sigma theta, we have sigma theta plus del sigma theta del theta over length d theta acting over the area dr minus this multiplied by d theta by 2 as we have seen, that sine component of that, minus this is minus, so this is plus, or sigma theta is acting in the, so this is plus and this is minus. So, this is sigma theta, or this component, this is cos sine component is acting in the reverse direction of the radial direction. So, this is also is a negative and this is also negative. So, sigma theta times dr times d theta by 2. So, this is equals to 0. Hence, on simplification this gives that sigma r times r d theta plus del sigma r del r to dr into r d theta. Now, when we multiply with dr, we have plus sigma r dr d theta. Now, this particular term when it is multiplied with dr d theta, since we will have a term dr square, and since this being small we are neglecting that particular term, minus sigma r r d theta plus tau r theta dr plus del tau r theta del theta times d theta dr minus tau r theta dr minus sigma theta times dr d theta by 2, sigma theta dr d theta by 2 minus, again this particular term will have d theta square, so we neglect that, and minus sigma theta dr d theta by 2. Now, from these if we look into, we find that sigma r d theta and sigma r d theta minus, these two terms cancels out, tau r theta dr plus and tau r theta minus dr cancels out. So, we have del sigma r del r dr r d theta, sigma r dr d theta, del tau r theta del theta dr d theta, and minus sigma theta by 2, sigma theta by 2, if we combine them together, this is sigma theta dr d theta, and this is equals to 0 for the equilibrium of the forces in the radial direction. So, if we write it down then and divide the whole thing by dr d theta, then what is left out is del sigma r by del r plus 1 by r del tau r theta by del theta plus sigma r minus sigma theta by r, this is equals to 0. So, this is the equilibrium equation in the radial direction. Similarly, if we take the equilibrium of the forces in the circumferential direction, then we can write down the equation as sigma theta plus del sigma theta del theta times d theta over dr minus sigma theta dr plus tau r theta plus del tau r theta del r over, sorry, so this is d theta dr over the area r plus dr d theta minus tau r theta r d theta, this is equals to 0, and this gives us the expression finally after simplification as del tau r theta del r plus 1 by r del sigma theta del theta plus tau r theta by r, this is equals to 0. So, these are the two equations, the equation del tau r theta del r plus 1 by r del sigma theta del theta plus tau r theta by r equals to 0, and del sigma by sigma r by del r plus 1 by r del tau r theta del theta plus sigma r minus sigma theta by r equals to 0 is the another equations of equilibrium. So, these are the two equations of equilibrium, and these are represented in terms of the stresses as sigma r, tau r theta and sigma theta, and they are written in terms of the polar reference axis as theta and r. Now, these are the equations of equilibrium, and of course, please note that in this particular case we have not accounted for the components of the body forces both in the radial and circumferential direction. We have neglected the body forces. Hence, we have del sigma r del r as we have observed now plus 1 by r del r tau r theta del theta plus sigma r minus sigma theta by r equals to 0 is the first equation of equilibrium, and del tau r theta del r plus 1 by r del sigma theta del theta plus tau r theta by r equals to 0 is another equation of equilibrium. So, these are the two equations of equilibrium which are explained in reference to the polar coordinate axis system. Thereby, from this we can find out that what are the stresses that is referred in an axisymmetric bodies. Now, as I said that we encounter several kind of structural element where the stresses the boundaries may not be perfectly straight. You can have a curved boundary over which there could be stresses as the radial stress, or which can be described by the stresses sigma r and sigma theta, and if the loading on such body is symmetrical, you have a perfectly symmetrical body, we have loading perfectly symmetrical in its vertical direction, then if we take any cross section or any longitudinal section for that matter, if we take section through the diameter, at every section the level of stress will be the same. Hence, it shows that the stresses at any of these sections are independent on wherever we take the section. So, the stresses are independent of theta, and these kind of bodies are called as axisymmetric bodies. That means, these bodies are perfectly symmetrical with reference to the vertical axis, and for such bodies, if the loading also is vertical or and symmetrical, then any cross section we take, at each section the same state of stress exists, and this kind of stress system and the bodies we call as axisymmetric bodies. So, the bodies which are perfectly symmetrical with reference to its vertical axis, we call them as axisymmetric body, and for axisymmetric body, if they are loaded symmetrically, this is important, if they are loaded symmetrically, then the stress components do not depend on theta. The stress components do not depend on theta, and thereby at any longitudinal sections we take, the shear stress components are absent, because we have the symmetric deformation, and thereby the shear stress components do not exist. If we take the absence of the shearing stresses, then the equilibrium equations reduces to del sigma r del r plus sigma r minus sigma theta by r is equals to 0, where only the normal stresses exist and shearing stresses are absent. Well, we have tried to give an outline of the state of stress if we refer them in terms of the polar coordinate system. Earlier, in a stressed body, we have looked into that if we have those rectangular components of stresses, the sigma x, sigma y and tau xy, we have looked into how to evaluate the stresses at different point and on different planes. Now, if we try to represent the stresses on any plane in a polar coordinate system, where the normal stresses sigma r, sigma theta and shearing stress tau r theta exist, we have seen how to write down the equilibrium equations. Now, with this stress conditions in the background, let us look into that how to solve a number of problems. Now, this particular problem I had explained to you last time, and I had asked you to compute the stresses. Now, here if you look into that, in this particular point, at a point in a stressed body, the stresses given are on a horizontal plane, the normal stress is 60 MPa. On a particular plane which is inclined with reference to this horizontal plane at 45 degree, the normal stresses are 50 MPa, the shearing stress as 40 MPa, and on this horizontal plane we have shearing stress as 30 MPa. So, according to, and what we will have to compute is the normal and shear stresses which are acting on the vertical plane using transformation equations. Now, here the given values are sigma y, which is equals to 60 MPa, which is plus, tau xy is given as 30 MPa, and on this particular plane on which we have defined say sigma x dashed, the normal stress, as equals to 50 MPa, and the shearing stress tau x dashed y dashed is equals to 40 MPa. We will have to compute what is the value of sigma x, which is acting on the vertical plane, what is the value of sigma x, and correspondingly what is the shearing stress tau. These are the two values we will have to evaluate. Now, if you remember the transformation equations on any plane, which is sigma x dashed is equals to sigma x plus sigma y by 2, the normal stresses, plus sigma x minus sigma y by 2 times cos 2 theta plus tau xy sin 2 theta. Now, in this particular problem, the stress on the inclined plane is given, which are sigma x dashed and tau x dashed y dashed, and the normal to this particular plane is at an angle of 45 degree. So, theta here is 45 degree, thereby 2 theta is 90 degree. Now, sigma x dashed is given as 50. So, 50 is equals to sigma x plus sigma y by 2, and sigma y is 60. So, sigma x plus 60 by 2 plus sigma x minus 60 by 2 time cos of 90, which is 0, plus tau xy sin of 90, which is 1. Second equation is tau x dashed y dashed, which is equals to 40, is equals to minus sigma x minus sigma y by 2 cos 2 theta, sigma x minus sigma y by 2 sin 2 theta, which is 1, plus tau xy cos 2 theta, which is equals to 0. So, from this we get minus sigma x plus 60 is equals to 80, or sigma x is equals to minus 20 MPa. Now, if sigma x is minus 20, if we substitute in this equation 1 for sigma x value, now minus 20 plus 60 is 40, 40 by 2 is 20. So, 50 is equals to 20 plus tau xy, and thereby this gives you tau xy is equals to 30 MPa, which is of course is the obvious, which is the shear stress component in the horizontal plane. So, if we draw the element now on which the stresses act, we have on this as sigma y. Now, we have evaluated the stress sigma x and also tau xy. And on this plane, which is at an angle of 45 degree with the x plane, on which sigma x dashed and tau x dashed y dashed acts. So, these are the values of the sigma x. Sigma x gives you minus 20. So, here if you see that I have made a mistake, the stress is minus 20. So, that indicates that normal stress will be acting in the opposite direction. So, it will be a compressive stress, whereas sigma y is a positive which is acting outward in the positive direction, and tau xy is positive. So, the direction of tau xy is in the positive direction of y, as we have seen earlier. So, that is the solution for this particular problem. Now, let us look into another problem. In fact, this particular problem also I had given you last time to solve from your end. I hope you could do it. Now, here let me explain to you that what are the aspects which should be looked into. Now, this particular problem states that these are the stresses acting with the rectangular axis system, which are sigma x, sigma y and tau xy, and we will have to evaluate the principal stresses, maximum shear stresses with the associated normal stresses, the maximum shear stresses which are along with the normal stresses, and we will have to use Mohr circle to evaluate these quantities. Now, here if you look into the normal stress which is acting in the x plane is compressive in nature, having magnitude of 30 MPa. So, sigma x is minus 30 MPa. Sigma y, the normal stress on the y plane, is 10 MPa. So, sigma y is equals to plus 10 MPa. Then we have the shearing stress. Now, if you note, the direction of the shearing stress is opposite to the positive y direction. Also, this particular shear along with the complementary shear on the other face is causing a rotation in the clockwise direction, which according to our sign convention is negative, because if you remember in the Mohr circle we said that the shearing stress which are causing anti-clockwise rotation is positive. Now, since here this is a clockwise rotation, so these are negative shear. So is on this particular surface. Now, since this is causing anti-clockwise, so this particular shear is a positive shear. Now, if we try to represent this in the Mohr circle, then let us see how it looks like. So, this is the reference axis system, and as we have defined earlier, this is sigma positive, this is negative sigma, this is positive tau, and this direction is negative tau. Now, on the x plane we have sigma x as minus 30 MPa, so it is in this direction, and tau xy as minus 20, so this is here. So, we get the point somewhere here, which is sigma x as minus 30 and tau as minus 20. Then we have in the perpendicular plane, which is y plane, which is 90 degree with reference to the physical plane. Here in the Mohr's plane that will be 180 degree, and we have positive sigma y which is 10 MPa, and we have positive tau which is 20 MPa. Now, if we join these 2 points as per our convention, this where it crosses the sigma line, we get the center of the Mohr circle. So, with this as the center, O as the center and OA as the radius, we draw the circle. And this gives us the Mohr circle, of which the center is this particular point, and as you know, the distance of this center from the tau axis is sigma x plus sigma y by 2. Now, here sigma x is minus 30, sigma y is plus 10, that divided by 2, that gives you minus 10. So, this distance is minus 10 MPa, and this particular point refers to sigma x, which is from here as 30 is minus 30. So, the distance from here to here is 20, which is sigma x minus sigma y by 2. As we have evaluated earlier, this particular distance O dashed is equals to sigma x minus sigma y by 2, and sigma x is minus 30, sigma y is minus 10 divided by 2, which is equals to minus 20. So, this is from here to here it is 20, and this is tau xy, which is also 20. So, the radius or this particular distance OA is equals to root of 20 square plus 20 square, which is equals to root of 400 plus 400, and this gives us a value of 28.28. Now, 28.28 is the distance OA. Now, we are going to evaluate now the principal stresses. The principal stresses are, this is the maximum principal stress, which is sigma 1, this is the minimum principal stress, which is sigma 2. Now, what will be the value of the maximum principal stress which is acting on this particular plane? Is the distance from here to here, which is in terms of the Mohr circle is the radius minus this. So, here the radius is 28.28 MPa and this is 10 MPa. So, this is going to be equals to 18.28 MPa. So, sigma 1 is equals to, as we have seen earlier, is equals to sigma x plus sigma y by 2 plus the radius, which is sigma x minus sigma 2, sigma x minus sigma y by 2 square plus tau xy square, and this particular quantity is nothing but the radius, which is equals to 28.28. So, the value of sigma 1 is equals to sigma x plus sigma y by 2, which is minus 10, and this is plus 28.28. So, this is equals to minus 10 plus this 28.28. So, the stress is equals to 18.28 MPa. This is the maximum principal stress. And what will be the minimum principal stress? Minimum principal stress will act on this particular plane, which is sigma 2, which is sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 square plus tau y xy square. In terms of the Mohr circle, if you look into, the distance is this radius plus this distance, and this radius we have got as 28.28 plus we have 10. So, the distance from here to here is 38.28, and in terms of this equation, sigma x plus sigma y by 2 is minus 10, and this radius is 28.28, which is minus. So, in a combined form, sigma 2 is equals to the minimum principal stress as minus 38.28 MPa. From this particular diagram, if we look into that, this is the value of the radius and this is the plane where we get the maximum value of the shear stress, and this is the plane where we get the minimum value of the shear stress. Now, at this particular point, the value of the normal stress is this, which is sigma x plus sigma y by 2, which is equals to minus 10 MPa in this particular problem. So, the maximum value of shear stress is equals to the radius, which is 28.28 MPa. So, tau max, the maximum shear, is equals to 28.28 MPa, and the corresponding normal stress on this particular planes where the maximum and the minimum shear stress occurs, that is equals to the sigma x plus sigma y by 2, which is equals to minus 10. So, the normal stress on these planes act is equals to sigma x plus sigma y by 2, which is equals to minus 10 MPa. So, these are the values which we get. They are sigma 1, the maximum principal stress as 18.28 MPa, the minimum principal stress sigma 2 is equals to minus 38.28 MPa, the maximum shear stress tau max is equals to 28.28 MPa, and the normal stress which acts on the maximum and the minimum shear stress is equals to minus 10 MPa. Also, we can evaluate the position of these planes, the maximum, minimum, normal stresses with reference to the plane. Now, this is the plane which is representing the vertical plane. The normal to the plane coincides with the x axis, which we call as x plane. Now, with reference to this particular plane, we can, if we go in the anti-clockwise direction, this particular angle will give us the value, half of which is the orientation in the physical plane which locates the maximum principal stress, and perpendicular to that is the plane where this minimum normal stress acts. So, these are the values, and that is how we can compute the stresses using Mohr circle. Now, let us look into another problem wherein we had last time discussed the values of the octahedral stresses, and as I have told you in the beginning that octahedral stresses are the stresses which act on the octahedral plane, and octahedral planes are the planes which are equally inclined with respect to the principal axis sigma 1, sigma 2, sigma 3 axis system. Now, if we know the values of principal stresses at a point, we can compute the values of octahedral stresses. Now, sigma 1, the maximum principal stress, is given as minus 2 plus root of 10 MPa, sigma 2 as 1, and sigma 3 as minus 2 minus root 10 MPa, and we will have to evaluate the values of octahedral stresses. So, let us compute these values. So, we have sigma 1 as equals to minus 2 plus root over 10 MPa as the maximum principal stress. Then we have sigma 2, the second principal stress, as 1 MPa, and sigma 3 as equals to minus 2 minus root over 10 MPa. Now, as we have seen in the beginning itself that the value of sigma octahedral is equals to 1/3 of sigma 1 plus sigma 2 plus sigma 3. So, here the values of sigma 1, sigma 2 and sigma 3 are given. So, this is equals to 1/3 minus 2 plus root 10 plus 1 minus 2 minus root 10. So, this gets cancelled. So, minus 4 plus 1 is minus 3. So, this is equals to minus 1 MPa. So, this is the value of tau sigma octahedral, or the normal octahedral stress, and for tau octahedral we compute in this form that tau octahedral square is equals to 2 by 9 sigma 1 plus sigma 2 plus sigma 3 square of that minus 6 of sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Now, here sigma 1 plus sigma 2 plus sigma 3 we have computed as minus 1. So, this is minus 2 by minus 1 square, so plus 2 by 9 minus 6 of, we can substitute the values of sigma 1, sigma 2, sigma 3, and this gives you as 6 times sigma 1 is minus 2 plus root 10, sigma 2, sigma 3 is minus 2 minus root 10, and sigma 1, sigma 3 is equals to plus 4 minus 10. So, this gives you minus 10. So, the tau octahedral from this we get as equals to root of 78 by 3, which is equals to 2.944 MPa. So, this is the value of sigma octahedral and tau octahedral. Now, let us look into another problem where we will have to, now this is a supporting structure which supports a billboard. Many times we use boards, sign boards on which the advertisements are put, and these boards are supported by some steel structural systems, and these boards are subjected to the wind pressure. The wind pressure, when it comes on the board, eventually it transfers the force onto the supporting structure, and this is one of such supporting structure in which we have a framework and all the members are connected in a pin joint, and this is the force which is acting on this member. Now, our job is to find out the stresses in each of these members from this particular force. So, what you need to do is that first we evaluate the forces in each of the members which are arising from this external force, and thereby we can compute the stress. Since the cross sectional area of each member is given, the force divided by area will give us the stress. Now, if we assume that this angle is theta, then this being 6, from similar triangle we get this as 3. So, eventually this is also theta, and if we drop a perpendicular here, this is theta and this is also theta, and the values of cos theta is 4 by 5. This particular length hypotenuse, this being 3, this being 4, this is 5, and so is this, this is also 5. So, the values of cos theta is equals to 4 by 5 and value of sin theta is equals to 3 by 5. Now, what we need to do is to evaluate, to draw the free body diagram and evaluate the forces. One section we can take here to draw the free body diagram, another section we can take here to draw another free body diagram, and we can compute the forces, and once we compute the forces we can find out the stresses. You try to compute the stresses for this particular problem. I will discuss in the next class so that you know how to compute the stresses. Well, let me summarize that what we have learned in this particular lesson. In this particular lesson, we have tried to look into the stresses which we have evaluated earlier with reference to Cartesian system, sigma x, sigma y, tau xy. Also, we have tried to look into that if a body which does not have the straight boundary, and if there are curved boundaries, how to represent the stresses sigma r, sigma theta and tau r theta, which are in terms of polar coordinate system, and also from there we have seen how to evaluate the stresses for axisymmetric bodies. Also, we have looked into some of the examples to demonstrate that how we can evaluate stresses at any point on a stressed body, either using transformation equation or by the use of the Mohr cycle. Also, we have tried to see that how to compute octahedral stresses on a particular stressed body, and keep in mind this octahedral stress is useful when you talk about the evaluation of stress in the inelastic stage, when it goes beyond the elastic stage. Now, this particular lesson was the last of the in the series of the module stress analysis. Now, we have computed or we have looked into the 6 lessons. We have looked into the 6 lessons in this particular module on stress analysis, and these 6 lessons, if we look into chronologically, in the first lesson I have tried to give you the general concept of different kinds of forces and what really is the meaning of the subject strength of material. So, it was introduced to you. Subsequently, the second lesson we had tried to give you the concept of the normal and the shearing stresses, and how to evaluate the equations of the equilibrium from the stresses that are acting in the Cartesian system, sigma x, sigma y, tau xy. In the third lesson, we have tried to evaluate stresses on any arbitrary plane. If you have any plane which is oriented at an angle of theta with reference to the x plane, and thereby we had arrived at the values of the stresses which we define as Cauchy stress formula, and also we have tried to evaluate the maximum normal stresses which we have defined as principal stresses, and these principal stresses which are acting in the principal planes. So, we have tried to locate these principal planes also in this particular lesson, and we have demonstrated that through a few examples. In the fourth lesson, we have evaluated the stress on any plane using transformation equation. In fact, we have discussed this in this lesson as well, that how to evaluate stress at any plane using transformation equations or using Mohr circle. We have seen these two kinds of problems in today's lesson as well, and in the fourth lesson we had discussed in detail how to construct a Mohr circle if we know the stresses at a particular point in a body. In the fifth lesson, we had tried to give you the concept of the octahedral stresses, and also we had looked into how to evaluate the stress at a particular point in a stressed body at different planes. And as I have told you, the concept of the octahedral stress, that this particular stress is the stresses which act on octahedral planes which are equally inclined with reference to the principal axis system, and these stresses are useful when we talk about the evaluation of stress in the inelastic stage. And in this particular lesson, we have tried to give you the concept of the stresses in a polar coordinate system that you have already looked into. Now, having looked into these aspects of stresses, let me pose some questions for you, and these questions are that what are the equations of equilibrium in Cartesian coordinate system of a stressed body? What are the equations of equilibrium in polar coordinate system of a stressed body? And what is the value of maximum shear stress if sigma 1 is equals to 10 MPa, the maximum principal stress, and the minimum principal stress sigma 2 is equals to 0. Now, these questions not necessarily you will get from this particular lesson alone which has been discussed at this moment, but looking into all these lessons whichever have been discussed on